Hello, and welcome to Answer Everywhere. Today we're taking a look at TCC, the TinyC compiler, also known as TinyCC. And I'm not sure that I've ever really even heard of this. This was a fan request, like all of the ones I've been doing lately. And I expect it to be a C compiler that's tiny. I went ahead and opened it in Emacs. I figured maybe Emacs would be the place to look at this. They have a Git repo on GNU Savannah. This doesn't provide, in my opinion, like a great UI for browsing code. So let's try Emacs. We've looked at a couple of C compilers before. We've looked at LLVM. I don't think we looked specifically at Clang, but we did look at GCC. And I'm going to guess that TCC is going to differ in a few ways. One is it doesn't have to be a general purpose compiler the way that GCC does. And two, I'm going to guess it does fewer optimizations or other fancy tricks. So it's probably going to be more about the standard flow of parsing, tokenizing, and all of that sort of stuff. I'm not quite sure where to start. We do have a README, and we have a makefile. Small. You can compile and execute C code everywhere. For example, on rescue disks. Okay, so I don't know how small a rescue disk was when this was first written, but it could have been like a floppy. Fast. TCC generates optimized x86 code. No bytecode overhead. Compile, assemble, and link about 7 times faster than GCC 0.0. Unlimited. ISO C99 compliant. 1999. TCC can of course compile itself. And safe. TCC includes an optional memory and bound checker. Okay, so we have these installation instructions and some makefile. We assume here that you know ANSYS. Look at the example ex1.c to know what the programs look like. And you're going to include the file tcclib.h. It can be used if you want a small basic libc, including, I guess, support for especially useful for floppy disks. Of course, you can also use standard headers, although they are slower to compile. Okay, so they have some a small basic libc. They have some version of libc that is reduced in size so that you can compile it onto your floppy disk, which I expect that you're not doing in 2024. And you can begin your C script with this shebang on the first line and set its execute bits, chmod a+x, and then you can launch the C code as a shell or Perl script. That's kind of cool. So you just write some C program that I guess takes only one file, or maybe you can include other files. But I guess maybe in your main or whatever you can run it like a script, and it will just compile it on the fly or something. Okay, so maybe let's look at example ex1.c. So they have this shebang thing here, and we're going to just run main print hello world. See, they have other examples that are more involved. Maybe example 4, we have Fibonacci. And this is the recursive Fibonacci implementation. And you're going to take, I guess, an argument and call Fibonacci on it. What is 2 here? So fib takes one argument. What is fib n2? I'm not sure. I don't know what this seems like this version of fib is taking 2 arguments. Am I missing something? Let's ask ChatGPT. Tell me about this program. How does fib n2 get called? It seems to call a fib that takes 2 arguments, but fib is defined to only take 1. Yeah. It takes one argument if n is blah, 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 blah. In the main function, program checks blah, 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 blah. It can calls fib with an n and an additional argument 2. The function fibn2 passes 2 arguments to a function that is designed to accept only one argument. This code will lead the compiler error. Okay, because the function fib is defined with only one parameter n. Okay, so that's an extremely long-winded way of saying, yes, this seems to be a bug. Okay, fine. Some bug. I don't really know where to start. Maybe we will start with TCC run, TCC lib. Let's mark just a few of these. So gen lib macho. I don't know what that could possibly be. Anything that has a small number of letters could potentially be interesting. x86-64 assembly is probably interesting. Gen, I'm not sure what gen will do. Maybe generate something, generate what, I don't know. But this should be linking, x86-64 linking. TCC talk, I don't know what talk could be. Macho, I guess we'll potentially take a look at Macho. When I'm on Emacs, I don't have I can mark files. I don't have the like queue or stack structure that I get with browser tabs. I'm sure I could find a way to do it. tcc.c is probably an important place to be. Also the header file, elf.h. And I guess maybe i386 assembly might be more bounded in a useful way. And then we have this include directory, which seems to be maybe stuff for what you might call like standard library stuff. So float is I'm going to get some sort of floating point implementation. Standard arg maybe about arguments. Bool is I had forgotten that somebody pointed out in one of the comments that C for a while didn't have booleans. So a lot of older C things had instead of doing booleans used integers. And I don't remember exactly how they ended up doing it. I think it may be in the standard, but it's only as a library as opposed to like in the language itself. Is bool a native C type? It exists in C99, but not in C89/90. The native type is called _bool, while bool is a standard library macro defined in standard bool.h, which expectedly resolves to _bool. Okay, so I guess it is, by 99, it does get built in. And I think before that, people just implemented their own version. And then whatever TCC defs is, TG math, I guess we'll look at var args. I guess maybe why not? Standard no return. I'm not sure. I don't think we're going to get to all of these. I'm going to try to keep this like down to an hour. We have this lib directory. These are alloca. I think these are just allocators. These are now C files as opposed to header files. We could look at run main, tcov. All of this is potentially interesting if you are into C. So I think that the real benefit here might, from like an educational point of view, might be that you get to see kind of like bounded complexity implementations of functions that you would use day to day if you were programming in C. Oh, you know what? Talk must be tokenized. So here's arm talk. I'm just going to, like when you're brainstorming, I'm going to generate a lot of marks of files, and then there will be a separate winnowing process. Dwarf is support for dwarf. I forget exactly the difference between dwarf and elf. They're somehow related. I think they're puns. How about Unix? I think, okay. So elf is extensible linking format. It's a standard file format for executable files, object code, shared libraries, and core dumps. Okay. And what about dwarf? Dwarf, a format for debugging data. Okay, so dwarf is debugging data. I don't know if it's specific to elf. It was originally designed along with the elf format. Okay. So maybe, maybe we'll take this opportunity to take a quick look at elf. Do they have a file layout for us? This seems to be it. We have the section header, and we have a program header, and we have, wait for it, a file header. Is that the first one? Okay. So here's the file. I'm sure many of you may, some of you know this well, and you're like, shut up. And others of you, I think you haven't really seen this ever before. Okay, so an ELF file has two views. The program header shows the segments used at runtime, whereas the section header lists the set of sections. So two views, I'm not sure what two views means. I'm going to guess these are both kind of indexes into the same data in the same way that maybe a table of contents is one index into the contents of a book. That might be more like sections, because those are kind of like sections of the book, and then you might have an index or a glossary or something else that indexes the contents of the book. And I think that's kind of perhaps what it means by views, but we'll see. So we have the ELF header. It's going to point down into stuff, including the text data, the .row data, which might be relocation, but I guess we'll see. And then the .data, which I think is non-text data. And then we have the section header table, and that also kind of points into the same area. This kind of looks XKCD-ish. See if we can open a larger version. Okay. But simple.arm, I guess this is some ARM file maybe? This is, I guess, too much detail for me to look at, and the font is too small. And I think I can probably download the original, but I'm not going to. Okay, so the file header defines whether to use 32-bit or 64-bit addresses. It contains 3 fields that are affected by the setting and offset other fields that follow them. The ELF header is 52 or 64 bytes long. All right. So we have a bunch of offsets and a bunch of sizes, and these are kind of like just indexes into, you offset by this much, and then you gulp this much data, and that's going to give you some known thing. This is basically some magic number, I guess, probably telling you like version, what is the file, etc. We have some byte that tells you whether it's 32 or 64-bit. We have some byte to tell you about endiness, I guess maybe of the data. I'm not sure. And then some version stuff, look like backward compatibility stuff. And then we have some maybe single byte. Yeah, single byte that identifies the target operating system ABI. And there's not a lot of them, actually. We have how does nonstop kernel get its own? I mean, there's not a lot of them because it's a single byte. But we have System 5 or System V. I don't know how people pronounce that. Linux, NetBSD, HP, UX. A lot of this stuff is basically gone, right? Solaris, I don't know if Solaris is still around. AIX, GNU Herd has its own FreeBSD, etc. I'm not sure, for example, what Microsoft. I guess Microsoft doesn't use this. I don't know if OS X does, or Mac OS, whatever it's called these days. What is Nonstop? Nonstop is a series of server computers introduced in 1976. Okay, at any rate, this is ELF stuff. I'll keep this open. Let me find Dwarf debugger. Debugging, I guess, format as opposed to it. It's not like a debugger in the same sense that GDB is. Okay, and we were not browsing here. We were browsing Emacs. Okay, so there's some Dwarf stuff. We have some ARM assembly stuff. All of that's fine. So let's stab. I'm guessing stab might be stable. Should we look at risk? Yeah, let's look at risk. Why not? We're doing it all. Okay. How many header files do we have? Not a lot. And then what were the header files include again? So I guess let's start maybe with tcc.c, the TinyC compiler. So including tcc.h. So where's that? Oh, it's here. Let's start with tcc.h. That's what I meant to do. Okay, so we've got a bunch of if-def stuff. We might be in Win32, which is like 32-bit Windows. We've got a bunch of comments that seem kind of like commented out. I guess if you want to do parser debug, you like uncomment this or whatever. And something about target sections. You might have a use different code generators for i386, x8664, so on and so forth. All right. Okay, so the default target is i386, which is like a 32-bit like Intel or AMD, I believe. I'm not sure. I think, I don't know, definitely Intel, possibly AMD. Okay, so this is just some defined stuff telling us basically which things to load, more or less. And then we're going to include a few things like libtcc.h, elf.h, stab.h, and dwarf.h. Where's libtcc.h? Let's open that here on the right. Okay, so we've got pubfunc, which are functions used by tcc.c, but not in libtcc.h. Okay, I don't know why, but let's kind of scroll down to see if there's actually any implementation stuff or if it's all macros all the way down. We get some structs. We have a token hash size, must be a power of 2. 16384, I'm not sure which power of 2 that is. But let's find out. Do I have factor installed? First of all, let's start Gwake. Why not? And try to factor this number. Okay, how many 2s is that? This is not the easiest way to do that, I guess. What if I just echo this and pipe it into word count? 14-ish? Do I have R? Yeah, okay, so 2 to the 14, fine. Okay, then we have, finally we have a struct, which is a token sim, which is token symbol management. We have, let me close tcc.h on the right for a second. So we have some next, some hash next. I guess this is the next hash in this list structure. We have some symbol stuff, sim define, sim label, some struct, sim identifier. And these are pointers. Direct pointer to define. I'm not sure if this is I guess maybe a define in the sense of like this thing. We have a direct pointer to the label. Or it might be like like where the thing is defined, I'm not sure. Direct pointer to a structure. I'm guessing structure meaning like a struct. And a direct pointer to identifier. And identifier, I'm guessing is the symbol, like like token sim is the identifier. And then we have the token number, the length of what, I'm not sure, maybe the length of the token, and then a list, this is car of str1. So I think that this is a, what's the word? Array of length 1 of characters. I'm not really sure what that's for. So let's find out. Yeah, so it's like a single character, essentially, morally. An array named stir of characters with size of 1. Yeah. This has limited practical use due to its size. Typically, if you want arrays to be large enough, so why not just use this? Why not just use? Why not just use car? Yeah, it says it's an array named string capable of holding 1 character, right? But it reserves memory for 1 character. And then car stir declares a single character named stir and reserves memory for 1 character. Car stir is sufficient, however, if you anticipate needing to store more than 1 character, or if you want to treat the data as a string, which requires a null terminator, then you would use an array. Okay, so maybe they just want it to treat it as a string, Maybe for somehow they're going to expand it or whatever. I don't know. Okay, and then we have a struct C string, a C string struct, which is just going to be like, I guess, a fancier string. It's got a size, the amount allocated, and data, which is either a car star or a new car T star. I don't know what new or NW car T star is, but this is basically a string that knows how long it is. That's the sort of string that you have, I think, in C++, but definitely in a lot of other languages, as opposed to the C style strings, which are null terminated. So if you want to know how long a string is in a null terminated string, if you want to know how long a null terminated string is, you have to iterate over the whole thing and find the terminating character. Whereas for a string like this, you can just look at the size. Okay, and then we have some type definition for a C type. So this is, I guess, going to be a model of C's types because we're writing a compiler. That's my guess. So we've got some int for T. Maybe that's just the which type is it. We're going to just enumerate the types with numbers. And a sim, which is ref. And the sim we saw before, I think. No, we saw token sim. What is sim? Sim is... Did we miss it? We get this type def struct sim in the test file. Yeah, okay, so sim was done here, but let's look at sim because it seems pretty fundamental. Okay, so we have type def struct sim. We have the symbol token, which is just some int. So we've enumerated the tokens and we're keeping track of it so we can look it up in whatever token structure we have. And we have an unsigned short R, which is some, I guess, an associated register. So we're going to keep track of, I don't know exactly what the mapping between symbols and registers would be, but we've also got this lval stuff. VT const, VT local, and lval type. Not the state of Vermont. C compiler. VT. So this might be just a TinyCC thing. The value stack. When an expression is parsed, its value is pushed on the value stack or vstack. The top of the value stack is vtop. Yeah. Each value stack entry is the structure S value. Okay, so we have, but what are these? So vconst means that the value is a constant. Vlocal indicates a local variable pointer at offset. At offset svalue.c.i in the stack. Okay, so vt local is just some local variable. And then we have lval, which I'm going to guess is left value. Lval is a flag indicating that the value is actually an L value. A left value of an assignment. It means that the value stored is actually a pointer to the wanted value. Okay, so we're storing a pointer to the value because we're on the left side of an assignment. I didn't realize that standard C had L values and R values. I thought that was like a C++ thing. Some programming languages use the idea of L values and R values, deriving from the typical mode of evaluation on the left and right-hand sides of an assignment statement. An L value refers to the object that persists beyond a single expression. An R value is a temporary value that does not persist beyond the expression that uses it. I didn't know that C had L values, but let's ask. Does C have L values and R values? Yeah. Okay, that's enough. Hush, hush, hush. So when were they added? Okay, so they've always had them. Okay, so I thought I read something the other day saying that L values and R values were like new in C++, but I must have either read it wrong or the person I was reading was was wrong or something like that. Okay. So we've got, I don't even remember where we were. Okay, so we've got this struct symbol. We've got some sort of indication of what the token is. We're keeping an int for it. And we have, we're keeping track of the register, which we saw. We've got some symbol attributes. And we've got this union here, which is a union of what? So we've got, on the one hand, a struct, or we might have a long enum thing, a long, or an int list, essentially an int array. And alternately, we might have another sim struct. And what are these things? So this struct is, I guess, some nameless struct that has an associated number or ELF symbol index. And it has another union, which might be a symbol scope, or I guess this is the scope level for locals. So we're so programming languages have scopes, and I guess we're just keeping track of where we are by maybe incrementing the scope every time we see like a function call or whatever. And then a next, keeping track of the jump label and some function attributes, and an aux type, I guess auxiliary type, which is some bit field thing. It says bit field access type. I don't know if that's like permissions or if you're just able to use it for whatever you want, given the type of symbol or whatever. Then we have this, so it might be one of those, which seems like if it's one of those that we're basically doing bookkeeping and maybe ready to generate assembly. Or if it's not one of those, it might be some long, which is, I guess, an enum value. So we might be part of an enum. I guess that's what we do if we're like some enum member. And then we have this also possibly defined token stream. I don't know. I don't know what that is. And or we might be next cleanup, which is a sim. I don't know, some sort of cleanup symbol. I don't know if this is for like symbols that are somehow paired, and who knows? Maybe we'll see that later. And then we have a C. So in the sim struct, we have a C type, which is the associated type. So like, I guess stuff like int, or if you, or float or whatever. And then we have another union of one thing could be the next symbol, the next related symbol for fields and anoms. Anoms or enums? Anoms. Maybe enums. So you might have a next related symbol. You might have an expanded token stream. You might have an assembly label. You might have some cleanup state, I guess if you need to clean up, and you might have some VLA array code. VLA array string. What's a VLA array? We have the very large array. No. I don't know. Maybe we can take a look. We can search for this, I guess. Or maybe not. I'll ignore that for now. And then we've got a previous symbol in the stack and a previous symbol for this token. Okay, I don't know why the token would have multiple symbols, but I guess it might. And then we have the section definition, which is, I guess, going to be part of the thing that we populate the ELF data with. And we have things like data offsets and what the data is, the section data, which is just an unsigned car star. I guess the amount we've allocated, which is used for realloc handling, allocation stuff. And then we have some TCC state and some section name, section number, etc., flags, etc., etc. And inside of section, I guess, recursively have other sections, which are like, we can have a link to another section, a section for relocation, a hash table for the symbols, I guess like a lookup table, and the previous section in the section stack, so that we can, I guess, crawl up the stack. And then finally, we have the section name. And then we have a bunch more defines, like sim struct, func new, func old, func ellipses, an ANSI function prototype with ... Is that like var? What's it called? Like variable. Like, so how about C function ellipses? I think it's for variable length arguments. What is the ellipses operator? Represent a variable number of parameters to a function. Yeah, okay. All right, and then do we have anything else after the defines? We have some code, maybe. Okay, so this is a huge struct for TCC state. So I guess this is like the God struct for keeping track of state while we're compiling. Some of it's stuff like verbose, nost, nick. You know, things like, do we have standard headers or not? Should we be statically linking? Are we exporting all symbols, etc.? What's the file type? Whether we're optimizing. So just basically, like, you would store this. These are like, you know, options. You would maybe store this in JSON if you were building a similar app in another language in 2024. We have other options here, like MS extensions. I don't know what that is. Leading underscore. Car is unsigned. I guess some options allow you, some versions of C or whatever allow you to use, change whether car is signed or unsigned, or whether you can use dollars and identifiers or whatever. Then we have warning switches, like whether you want to enable warnings on various things. And this is just like, you know, this seems like a lot of just options. What is this called? This is called like TCC state. Where did you go? Okay. But we should have other kinds of state too, right? I hope. Okay, so yeah, so we have like here we're recording the TCC lib path, the SO name as specified on the command line, the R path as specified on the command line. So these are things that you pass into the compiler. Output type, whether, I guess, to test to run with DT. I don't know what that is. I don't think that's running test. Maybe it's some sort of like dry run. We have an array of all the loaded DLLs. We have all the include paths and library paths and so on and so forth. Some error handling stuff. And then this section is just called compilation, but we have some buffered file, which I'm going to guess is a file maybe with a buffer as a just as a optimization. This include stack thing. So some stack of includes, I guess, and an include stack pointer, which is a pointer, I guess, to the, I don't know, some presumably where we are in the include stack. Some stack of if defs, and some, I guess we might cache and or hash the includes, etc., etc. We have a stack of pragmas, it looks like. And what else? Some inline functions. They are stored as token lists and compiled last only if referenced. Okay, so we may not compile inline functions. I guess we only do if they are actually called. And then we have keep track of some sections and some private sections and some predefined sections like text, data, row data, and BSS. I don't think we saw BSS, but we saw rotated data in text. And then we have some bounds check stuff. So we have bound section and L-bound section. Bound section contains global data bound description. Okay, and then L-bound section contains local data bound description. I guess these are maybe like data areas for global versus local variables or something along those lines. Local being ones that only make sense, I guess, in some contexts. And what else? We've got some dwarf stuff down here, whatever stab is. Stab seems to be under debug. And then some test coverage, which I guess the compiler has to keep track of somehow. And if there are new undefined symbols since the last new undef symbol, we'll keep track of that here. And so on. Okay. All right, so this is all compiler stuff. This is looking good. But let's take a look at, was it libtcc.h? This is potentially another fundamental file. We have some stuff about allocators, like set custom allocator for all allocations. We're gonna at least name the type def struct here so you can import it or whatever. And I guess this is just kind of like the public API. TCC add library, add symbol, add output file, relocate, etc. Okay. All right. So we look at tcc.c. We've got some help string. And we've got main. So main, we're going to create the TCC state, which is like the God object that we just saw. And create some things like ret, I'm going to guess is return, opt, maybe options, start time, end time, so we can keep track of how long things take, and arguments, etc. Redo. I don't know what redo is, but we're going to try to parse args and do some various things depending on what the args are. And it looks like maybe the behavior is interspersed with the argument parsing, which we've seen in some a few older repos, but I don't think is the style so much anymore. Okay. Actually, a lot of the stuff that's here seems to be like about errors. So maybe this is just erroring out. We set environment with S. I don't know what S is, but I guess we're like starting to prepare to do work. First file equals null. Compile and add each files or library. So we've got this do block, do while we're not done, and while S output type is not TCC output obj, and S option R. I'm not sure what option R is, but maybe this is maybe the last thing that's output is the output obj. Okay, so we get the file. We take a look in S files. S is like the is that the state? S must be the state, right? Yeah, S is the state. Okay. So we get the files, we look, so the state has a bunch of files that we're going to compile. We get one and we set it, we set the S file type, the state file type, to the type of the individual file. So I guess S file type is like the kind of like, what file type are we currently working on? And if it's an AF type lib, AF, I'm not sure, but some kind of library, then we'll set ret to TCC add library error. So there seems to be some sort of error. Otherwise, if we're verbose, we might print some stuff out. If we're not the first file, then we'll set the first. Okay, so if the first file hasn't already been set, then we'll say that we are the first file. And then we'll call TCC add file to S, the file name, and set ret to that. And done means thread is populated, which I guess we did here, then done will be true, right? Or we're going to increment n, and if it's bigger than or equal to the, I guess nb must be number of files. Does this compile? It says compile or add files or library. So where's the compiling? Is it TCC add file? I don't know. Okay, so we might be doing benchmarking, in which case we get some sort of clock stuff. If we're running tests, then I guess we're running some sort of tests. And if we get down here, then we say done is 1. And if t, then done is 0. This is, I guess we have more tests to run. I'm not sure where those variables are, and then we're done. So maybe maybe TCC add files. So if we're not first file, then we do this. But otherwise, regardless, we add files. So maybe this is the function that does compiling. So let's take a look at TCC add file. It's going to take some state and some file name. And we're going to get the file type. What is AF type mask? AF type. AFF. What is AFF? I don't know. So we might, so I guess we are going to use a file extension to detect the file type. And if the extension is at 0, I guess, so if we have some extension, we're going to increment it and compare it with the known extensions. So S is ASMPP. What is that? ASMPP, some assembly. How about ASMPP file type? It's something. I don't know. S is an assembly file. C is a C file. H is a header. I'm not really sure. But if it's one of those, and we see the file type is the A must be some, I don't know what A is, but F type. F type must be file type. AF, I don't know. But we say it's a C file type. Otherwise, I guess we decide that it's a binary file. And if there's no extension, we assume that it's a C file type. And then once we've just determined what the what kind of file it is, we call add file internals. Add file internal, and we pass in the state, the file name, the file type, ORed with this error. Maybe this flag about whether to print an error. And so what does this internal function do? We check the target OS. We might, if we were in OpenBSD or Win32 is not defined, I guess, then we create this 1024 sized car buffer and do something with TCC glob SO. Not really sure what that's about. We'll ignore binary files with if the -e flag is passed in. Then we'll open the file calling TCC open, which is presumably just some wrapper around whatever the OS open thing is, and get a file descriptor. If we have no valid file descriptor, we'll error out. Then we will set the current file name to whatever file name we have. We'll look at the flags, and if it's a binary file, then we'll call elf-w e header, or no. We're, I guess, creating an e header thing with whatever this is. And we're calling TCC object type on the file and the e header thing and getting an object type. And then we're going to seek, calling lseek into the file descriptor. 0, I guess 0 bytes in and whatever seek set is. I guess we're saying that we're going to look that much into the file and setting the seek there. Let's look at lseek. lseek. This might just be the equivalent to like rewinding the tape. So maybe the file is seeked somewhere and we want to just rewind it to the beginning or something. And then we're going to switch on the object type. If it's a bin type rel, then so somehow this is like refined our object type. We knew it was a binary, and it might be a rel, maybe relative, or an AR, like archive binary. And depending on that, we're going to call an appropriate function. And but we don't care about binary files, do we? We don't care about macho. I want to see where we actually call the CC file stuff. Now, what was that called? AFF type C, I think. What is this function? args parser list file. No, I want the function that I was at, but this is where I was? I think this is where I was. This is TCC add file internal. So in here, let's see how big this is. I'm forgetting the this command here. Okay. So do we get type C in here? Oops. Yeah. Okay. So if we are type C, then oh no. No. I guess are these so add file internal. We have this if flag for whether we are a binary, which is what we just saw. And are we still in the if here? I think so. So if we go down, what's the next thing at the same level of granularity? We're checking a bunch of things like TCC is native, what kind of binary type, what's the target type. So maybe we do want to look at some of this. So this is where we do things like loading the archive, loading an object, which I think that maybe we just saw before, but okay, so down here finally is when we get the else. And if we're, I guess if we're not a binary file, this is what we do. We call it dynarray add and then TCC compile. So dynarray add should be just some adding stuff. Dynarrays. Not really sure what that's doing, but some array. And then this is where we were. I think we were here. Sorry, I got a bit moved around. So somewhere there's this TCC compile function, which I want. Let's see if we can find xref, find TCC compile. What if we just do grep? Okay, so here's TCC compile, or at least compile sem. I want just a regular compile here. There we go. Compile the file opened in file. Return non-zero status. Return non-zero if errors. Here we enter the code section where we use the global variables for parsing and code generation. TCC pp.c, TCC gen.c, and target gen.c. Other threads need to wait until we've done. Okay. Okay, so we call TCC enter state S1. What does that do? This is some jump thing. Okay. And we say that the set jump is enabled, and we maybe do some error stuff. If we don't have a file descriptor, then what? We set length to the length of the string, open bf string length. I guess we're kind of like opening the file or copying its memory. Otherwise, we somehow open the file. I guess probably bf might be the buffered file thing that they defined. Then we call preprocess start. This is, I guess, invoking the preprocessor. And then TCC gen init. So maybe this is like initializing the generator that's going to generate what? Maybe generate assembly. I don't know. And then if the output type is output preprocess, then we will invoke the preprocessor, which we started here. Otherwise, we're going to call TCC elf begin file. I guess like kind of opening or starting the elf file. And then we'll check the file type. And we'll AND it with a assembly or assembly pp. And I guess if that goes the way we expect it to, then we'll call TCC assemble. Otherwise, we'll call TCC gen compile. And then we'll end the elf. And we'll call it TCC gen finish, etc. So I guess it's worth looking at least a couple of these. I think that let's just maybe open another buffer to the right here and kind of keep this thing to the left as a reference. Oh, can I not do these font sizes separately? Bummer. Thank you, Ediac. I appreciate it. How are things with you? I'll maybe move this to the side. Okay, so I want to look at a couple of these. I want to look at TCC preprocess for sure. That should be the preprocessor. So this should be, well, let me just grab this and make it into its own file. No, not that. Come on. All right, I'm gonna grab this. I don't know what's up with, why is this not copying? Something's wrong with my Emacs config, but I guess I'll just live with it. Good. I'm glad you're fine. Okay, so on the right here, we have the preprocessor. And okay, TCC preprocess. We've got this buffered file and some, I guess, tokens seen. This will be the number of tokens we've seen. S spaces, maybe, spaces level some string, essentially a car star, which is const, and car white of 400, whatever that is. Maybe white spaces? I don't know. And we've got some flags: parse flag preprocess, parse flag line feed spaces, except strays, etc. I think strays are like skeletons, but for the winter climates, if I understand Minecraft correctly. Okay, so we've got some stuff about line micro output, whether to do benchmarking. We're going to set token scene to be token line feed, spaces to be 0, and level to be 0. And if file prev, I guess if there's some previous file, then we will do some stuff with pp lines. We will, I guess, take the previous file and increment the level. I guess we've inferred by the fact that we have some previous file that there's some level above us, and we're incrementing it. But what I don't understand is, like, if we're 16 files deep, we will have one previous file, and it seems like we're maybe incrementing or whatever. I don't know what pp line is doing, I guess. So maybe we were looking at the previous file and thinking of it as a level above us, and that's why we're incrementing level. And then maybe there's some recursive call in here that walks up the chain. At any rate, then we're going to call pp line with the file and level. I don't know. Again, I don't know. I don't know what pp line is. But then we go in this infinite loop, and we're going to take a look at the include stack pointer and call next. I don't know what next is. This is TinyCC pp. So next could, I guess, be like literally anything for the compilation process. And if the token is, maybe next just consumes the next token or something. And then if the token is end of file, we break. Then we set level to S1 include stack pointer minus I pointer. Okay, so we're subtracting the I pointer was include stack pointer, but include stack pointer is not changing, and I pointer is changing. So I guess after we've consumed this token, we like reset the level by subtracting this thing. I'm not really sure why. If level is, I guess, non-zero, it might be positive or negative, though, I think. So let me ask and see, what does if -1 evaluate to? Evaluates to true. Any non-zero value. Okay. Yeah. So so we're like, it's like an elevator at some floor. I guess if you go up, that's positive floors. If you go down, that's negative floors. And so this is saying, like, are we on the main floor? And this says no. Well, are we above ground? And if so, then we're gonna do some pp line stuff, which again I don't know what that's doing. But I guess pp no, never mind. Forget that. And then some deflag stuff. I'm just gonna kind of gloss over this because I want to get to some other stuff as well. And we do things like check if it's a space, check if it's a line feed, which I guess is kind of like a new line. More pp line stuff. If pp needs space, then we'll set the white spaces at spaces ++ to the single space character. And then we're gonna I guess we'll set white at spaces to 0. Then we'll f puts will, like, I guess send the white space string to the ppfp thing, set spaces to equal 0, and then we're gonna get the token string from some token thing, I guess wherever we are in the parsing stuff, and put that in the S1 PPFP. And then we're going to set token scene to whatever pp check hex something or other token p. Yeah, so I'm not really sure what any of these functions are doing. Some of it, the general structure is a little bit clear just from what we know that the pre-processing step has to be doing. But pp maybe is parse. Let's take a look at pp line. Pre-processed line, pp line. So we've got this p flag about macros, etc. Yeah, I'm guessing that this is like pre-processed line and that this is doing the heavy lifting of like replacing. But I'm going to ask ChatGPT to explain this to me. And in fact, I'm going to start a new chat just so it gets a clean context. What does this stuff do? Do I stream early nowadays? Hello, Ayush. I've been streaming at 10, really 11-ish a.m. Eastern time. I don't know if that's early. It might be early for you. It's not super early for me, but it's also not late. I also haven't had a consistent streaming schedule lately. Okay. So here's what the function does. It calculates the difference, d, between the current line number and the reference line number. If a certain flag is set, the function immediately returns without doing anything. Depending on the value of p flag, some different actions are taken. Finally, it updates the reference line number. Oh, hang on. This is not. Oh, okay. So line macro output format none means do nothing, I guess. Else if level is 0 and the line ref is, I guess, non-zero and d is less than 8, then while d is bigger than 0, we do whatever this is. We put new lines in decrement d. I guess the first 8 lines are what? I don't know. For some reason, this is like 8 new lines or something. And then if we have standard format for the macro output, then we're going to fprint the thing in. No. What does fprintf? Does the format go first or the string? I forget in C. So the stream and then the format. Okay, so here's the string that we're printing. And then here's the format, which makes sense. And this is kind of just printing this here. Otherwise, it prints a hash directive to the output file with the current line number, file name, and a level indicator. Okay, so a line directive to the output file, the current line number. So what is a line directive and a hash directive? So the line directive explicitly sets the line number and source file name that the compiler will associate with subsequent lines of code. For example, line 10 myfile.c tells the compiler that the next line of code corresponds to line 10 of the file myfile.c. Okay. So that's, I guess, a way of when you is that so that when you expand the macro, like you could have a call to a macro that corresponds to like 30 lines of code, and so instead of changing the file so that you add 30 lines everywhere, it sounds like we just give an instruction that says like imagine this is the code at line 10. maybe, and then the rest of the file remains unchanged. Hash directives are instructions to the preprocessor that begin with a hash symbol. They are used to control behavior of the preprocessor. Yeah, but I thought that we were preprocessing, so why are we generating these? I'm not sure, but that's maybe what we're doing. Moving on. Let's take a look at TCC assemble. Whoa. Okay, how about this one? And you pass in do preprocess, and then we're just going to call debug start and set the current text section to text section, which is not passed in, I don't think, and we don't get it from the S1, so it just must be floating around. And we get the data offset from the text section. Set no code wanted to 0. And then we call assemble internal, which is what I really wanted. And assemble internal is going to do a bunch of flag stuff, including parsing flags. Horrible gas comment. While toke is not equal to toke line feed next. I have no idea what that is. We seem to be calling ASM parse directive if the toke is bigger than ASM dir first and less than ASM dir last. So there might be some ASM directive that is a token that has a certain number, and if we're in that range, we're going to call ASM parse directive. And if it's a token PP num, maybe preprocessor num, then we might do some stuff like get local label name. Else if it's in toke ident, which is I guess an instruction or a label, then we set opcode to toke, call next, and if toke is a colon, then we call ASM new label on the state and the opcode in 0 and call next, and then go to redo. I guess redo we saw before. Redo is like this is essentially like calling continue, but I guess I think that what we've done is since we're using gotos, this is like we're deep in a loop, but the loop is spread out over multiple functions, and by allowing a call to go to redo, I think what they're doing is essentially letting you go to the top of the loop from a separate function. It's a little bit like a more chaotic version of like coroutines where you can mutually call functions from each other. GoTo at least has the reputation of being dangerous. I don't know enough about when it's fine to use it appropriately. It may just be that it requires a lot of discipline, and that discipline is generally hard to come by. Okay, so otherwise, if token is bigger than or equal to token identity, it says instruction or label again, right? Or no, this is just what we looked at. Okay, or if token is the equal sign, then we're going to we'll call set symbol on the state and the opcode. I guess that's kind of telling, that's really all we're passing in. So somehow, S1's the state, right? Yeah. So somehow we're like, I guess under the hood, appending the opcode as like, this is the next thing that you're going to do. Otherwise, we're going to call assembly opcode on the opcode. So look at set symbol. Set symbol. So what I want to know here is what we do with a state. We're going to call ASM expression here, and elfsim highlight regex p s1 yellow. Okay. So really we're just calling ASM expression here and new label here. But we just keep going deeper and deeper. I'm not really sure if this is helpful. But at some point, we're basically generating assembly stuff and calling into eventually we have to call into one of the libraries that has like x86 or ARM or i386 or whatever. And this just keeps going deeper and deeper. This is TCC SM. How long is TCC SM? I don't know. But SM expression, we'll just take a quick look, I guess, while we're here. SM expert unary. We do not use the C expression parser to handle symbols. Maybe C expression parser could be tweaked to do so. So we're doing essentially some parsing, it looks like. Again, I don't know what ppnum is. Maybe I can look in the documentation. Tell me what ppnum is. Not that. I guess it doesn't want me to know. ppnum tokens. All right, how about the AIs? Let's ask Gemini. In TinyCC, what does PP stand for? As in, what is it? ppnum tokens or talk ppnum or pp line, I think it was called. My guess is preprocessor. Well, Gemini doesn't seem to know. What about ChatGPT? Preprocessor. Okay. All right. So we have some, I guess this must be a preprocessor token, or maybe it stands for something parser. I don't know. But we're going to parse a bunch of things. It could be a plus sign. It could be a dash. It could be a tilde or a period. Are there tildes in assembly? I386 assembly dash. I don't think I have much of a hope of searching for tilde. Format? Syntax? We have semicolons and commas for sure. I don't know. But whatever we're parsing, we might get some tokens that look like these. And if we get, for example, a left paren, then we're going to call next, and then take whatever I guess is the next token or whatever, and call ASM expression on it. And then we're going to skip the right paren. And I think this is ASM expression, right? Oh no, this is ASM expression unary. So this is probably almost a recursive call, but maybe to like a companion function as opposed to the function itself. Okay, so that's fine. And then let's look at TCC gen compile. And this might be the last thing we look at because we're at an hour and 20 minutes. Okay, TCC gen compile. We set the function name to the empty string. The func ind, I guess maybe func index to -1. The anon symbol, I guess anonymous symbol. But we have anon, anon, on the left side and anom, anom, on the right side. I don't know what that means. I don't know if that's that's intentional or unintentional or what. We do some flag parsing if we're in ARM, then we call ARM init. And what? And then we call next. And then we call decal of vtconst. Why? I have no idea. And then we generate inline functions. And then we check the vstack. Check it for what? Maybe just sanity check it to make sure there's no errors. And then we say that we're done with debugging and we're done with like test coverage, I think is what tcov is. And then we return 0. Cool. So next has to be the whole thing, right? Init, print, parse flags, next. And then then we're done. What is next? Next has to be the most important function. What is it? Find definition. Oh, this one, yeah. Return the next token with macro substitution. While macro pointer, so we've got some, so with macro substitution. So this is, I thought it was the C preprocessor's job to do macro substitutions, but maybe that's what we're doing here. So we have some macro pointer, and while it's non-zero, in fact, we start with a while macro pointer, and I don't know whose job it is to make sure it's non-zero. But here's redo. We set t to what the macro pointer is pointing toward, and if the token has value of t, so we're going to call it token has value on t, then we're going to try to get the token, passing in the macro pointer and whatever toxc is. And if the token is a line number, or if the token equals token line, okay, then we set file line num to toc.i and go to redo. I don't know what that's about. Maybe the line numbers are like encoded and we're just reading off the line numbers, ignoring them. I don't know. But then we're going to go to convert. What does convert to? I don't know. Else if t equals 0, the end of the macro, or unget token string, then we call end macro and continue. Otherwise, if it's token end of file, then we do nothing. If otherwise, we're going to increment the macro pointer. Check if we're above the token identity threshold, and then bitwise and it with the complement of sim field, which will, I guess, remove no subst marker. Otherwise, if we are a double slash, and then we check the parse flags and say that there's some stray double slash in the program. Then we set token to t and return. Okay, what is convert? No definitions for convert. Convert, oops. Convert preprocessor tokens into C tokens. So if t is equal to toc ppnum, then we possibly parse the number of the toc C string data. Yeah, I'm not really sure what this is doing, but some sort of C preprocessor token figuring out stuff. So this is interesting. It is small, but it's all kind of like wound together. You might consider this like an unkind view of this might be to consider it a little bit like spaghetti code. So it's not clear where any of the logic is. Seems like you kind of have to bob and weave through the code base to find out, you know, where is this actual thing? Like where's the parser? And how do I like debug something? It seems like there's a good number of go-tos and also just a lot of indirection in the form of function calling, where you kind of have to trace things pretty well in order to have a good sense of really what's going on. It's not a lot of it's not local, I guess is one way to put it. So you can't just look at a file and tell something coherent about the code. You have to kind of have a global understanding before you can really understand one local section of the code. But I said that, but I'm wondering if we can find just anything that looks like just a standard standalone parser. But maybe I'll just do a quick search for parse. We have the parse flags, and we've seen lots of parsing stuff. I'm just wondering if there's anything that looks like the sort of parser you would maybe write for a college course or whatever. Let's see, parse define, parse flags, parse hex or UCN, parse number. I think we saw that called parse all digits. Parse number in null terminated string p and return it in the current token. So this is just going to be some call to like this is going to be if car equals X or car equals capital X, then we're going to mess around with the state, I guess set B to 16, saying this is base 16. Otherwise, if we have the car is equal to B, then we're in binary base 2. So this is looking more like a standard parser in C, but this is just parsing the numbers. Do we parse anything else? Let's see. How about void parse underscore? Parse escape, parse string. How about parse string? We may have looked at this before. So if there's an L, then I guess it's is long. Whatever S is, maybe this is like white space or separators. Yeah, okay. If the separator, I guess, is a slash, then we do some stuff, including, and we have some what looks like a to-do to make it portable. XXX is not a good readable thing to put in your code. I put this in sometimes because XXX is easy to remember and it's unlikely to appear in code on its own. So it's really easy to grep for, which I suspect is why other people do it as well. I was pretty shocked when I saw somebody do this in the wild. All right. So this is some string parser, and this is looking more like a standard parser. But these are just like really small parts of the program. There's not. Okay. So I think I'm gonna basically leave it there. Let me do a quick look over some of this stuff to see if there's something I really want to see. I mean, maybe we should peek at one of these assembly files. They're basically defs. And I guess on the left side is like the macro, and on the right side is the thing. I don't know what you call this, the opcode itself. This is how all the assembly files look like. Let's look at was that gen? This is the RISC v64 gen file. And we've got some stuff like about registers. These look like pretty small functions. gsim adder, patch all branches in list pointed at, blah, blah, blah. Okay, so no, that wasn't. The first file that wasn't gen, it was assemb. Okay, so that's what the assemble files are. The assembly files are these things that look like they're just defining opcode. Let's take a look at the i386 gen. Is there a gen? Yeah, here. And what? It's about 1,100 lines long. We've got a mod rm reference. I don't know what that is. It contains the additional 3 opcode bits. So we're just kind of like working with opcodes. Whatever this is doing, while bytes minus minus. So while we have bytes left, we're going to call G on some opcode or whatever. Oh, this is filling with no ops. I should have read the function name. So a lot of like little stuff like this. So I guess you have to know what you're doing to implement one of these files. But so far, this looks totally understandable. This is basically like a giant table. Load. So load is going to do what? Whatever PE get import is. We've got a lot of masks. We're checking if things are local, and whether if they're L values and they're local, then we are setting v1 type to whatever, I don't know, and then we're kind of assembling something, whatever fr is, and then we're going to load vr and passing in the v1 thing. So that's, I guess, a recursive call to load. Load r from value sv. So I'm not really sure. Okay, so here it looks like we're dealing with assembly. So we've got this move 0 r. Oh, r must be register, right? That is this is probably loading something from a register. Okay, so stuff like that. Store must be storing it into a register, and that makes sense for the gen code. What about assembly.c? This doesn't seem to be much more interesting, although we do get some functions. You have things like parse operands, whatever mod rm is, mod remove something, I don't know. ASM rex. I guess Rex is the, what's it called? Register. Okay. And then is link interesting? So we might have relocation type. So it might be relative, got PC, got off. I don't know what these things are. I don't know anything really about relocation. But we're dealing with it here. Returns an enumerator to describe whether and when the relocation needs a GOT and or a PLT entry to be created. Okay, so this is stuff dealing so far primarily with relocation, it looks like. Is that the hardest part of linking, maybe? Is figuring out where things go. Relocate, relocate, relocate. Create a PLT entry, etc. Okay. And then we have token, and then maybe this is defining what the tokens are. So define token ASM, calling this def thing, but this double hash seems to be some sort of separator, x, b, and then this hash x is constant across all of these. So I don't think it's, oh, I guess it's like the argument that's passed in. But we have B, WL, WL, BWLQ. I don't know what these are. But some sort of stuff. What does def do? Def. Def of ID string calls stir, and then I guess null terminates it maybe. Is that what it's doing? TalkSM. Yeah, I don't know. BLW, BL. Let me look up BWLQ x86 64. I don't know if this is a TinyCC thing or a assembly thing. So move B, WLQ, blah, blah, blah. Okay, so move B, move W, move L, move Q. Move B leaves the upper bits unaffected. Move W leaves the upper bits unaffected. So move byte, move word, move L is, I guess, long or double word, and Q is quad word. Okay. So that helps me feel more oriented. I guess this is saying like in the code or whatever, I think we want to deal with this somehow. This I think is mapping the fact that the thing that we think of as move B is really called move B or something along those lines. Let's see if we can find a reference to BWLQ in the code. No. Okay. Let's try grep. So we see it in just the token stuff and the assembly. So I guess the only things that really know about these are the i386 files themselves. But these somehow define the tokens that the token stuff is operating on, and we saw elsewhere that as we were parsing, we were getting these sorts of tokens and dealing with them. And I think that's going to be it for TinyCC. And also, this was an hour and 40 minutes. With the kind of the way that the code is laid out and spread out. If you were to take another look at this, you could have a little bit of a clearer understanding of what's going on. But kind of my sense is that maybe it's a little bit easier to look at or understand a more modern C compiler that might be a little bit bigger, because the code will be written typically in a more modern style, that there won't be as many go-tos, and I think you'll typically be able to find something like a parser will be kind of more modularized, as opposed to, if I'm understanding correctly what's going on, and I'm not really sure that I am, it seems that like some of the parsing functions are kind of like hither and thither, as opposed to being kind of just in one place, and that makes it a little bit harder to reason about. But it is tiny, and you can run kind of like C scripts with it, which is pretty interesting. So I'm going to leave it there.